Yeah, it's your boy Chill here. Welcome back to Project Moisture. This is probably going to be the final video in this series. And we're going to do something that we haven't been doing a lot in this series. We're going to look at software, right? This is ostensibly a programming channel. Let's look at some code. And today's a little different because we're going to be looking at Python code. I got me in my Python IDE here, PyCharm. And yeah, we're going to take a look at Python. I am not a Python programmer by trade. So this is just stuff that I've hacked up here, but I had fun making this and I enjoy. Python was a pretty good choice for this project. It wasn't originally, my first choice. Of course, my first choice is going to be C++. That's just who I am, right? But it was just looking at like the tool chain and how to get access to all the GPIO on the Pi 0. I just like, this is just too much of a headache, and I don't want to deal with this bull crap. And Python is so easy, and the beauty of being able to do Python here was I could actually run it on my Windows machine and on my Pi 0, which is running Linux, equally in these different environments for testing, and it was just it's very nice to work with. So let's just jump into the code here. I'm just going to do a review of the overall architecture and how I implemented stuff, and then we'll call it a day. So as you sort of saw from, let me see, do I have it here? I think I do have it. Yeah, I got my my super professional presentation here. As you can see, the basic ideas here, we want a state machine. We've got these different I/O modules that are virtualized, and we got some we want to be able to have a real loop that runs on the Pi 0, but also a simulation loop that I could run on my Windows with all the faked I/O modules. And one big thing is we want to use exceptions and have a catch-all panic handler that makes sure we don't flood the house. If anything unexpected ever goes wrong, we just shut the whole damn thing down. We enter panic mode. Lock her down. So let's start at the beginning. We're going to start at the top level. We're going to work our way down. Main.py. Just a couple of quick helpers here. Make a object for logging, because we're going to log all the events, all the state changes get logged to a file so I can look at it later and just see what happened. And if something goes wrong, or just to see, when things have been failed. I could even, so I'm not going to do this, but I could create a tool that scrapes the log file and, generates graphs of when and how often the water was filled, water usage, etc. I'm not going to do that, of course. And here is a little handler just handling if a termination signal happens, which will happen if, someone tries to turn off the service. Because I got this, the program here is going to be running in the background. It runs in the background. It's started by another program called Supervisor, and that just runs this as a background service and makes sure if something bad happens, it could potentially restart it. Starts it when I boot the system, etc. And it also has the ability I can send a command to Supervisor to stop this process, and that Supervisor will then send a termination signal. And so this is handling that termination signal. And here we go. This is where we go in. Like, I've got a main here, and when I run, this is what it looks like normally. If I'm doing simulation, I just change the code here to call do simulation. But normally it's just main, the entry point, calls go, and off we are. We create our log. We log, hey, we're starting up. We also write to this. So this writes to log file. This writes to, just the terminal basically on the screen if you were to run the program, or this will output into Supervisor's logs. We set up our termination sigterm handler. We set up, this is a client connection. So there is a separate process on the system that actually handles the general purpose I/O on the Pi. It's called PigPio. I call it PigPio. There's Pi GPIO, but I call it PigPio. And we communicate with that via a socket. So we have our own connection to that service running on Linux. That's what this is. That's the client connecting to the GPIO service. And we have I/O, which is my wrapper around, input and output. So my wrapper uses the PigPio client to give an interface into the I/O services for my system. Like the let me think here, the valve control and the signals for low-level sensor, that sort of stuff. Flood sensor, that's all handled in here. And then we create our display that uses also the PigPio client because it's using I2C. We create the touch object, also uses the client. And mTouch input. That's interesting. So I believe this is the thing that represents the touch unit, and this thing wraps around that. So that's my virtualized interface for touch input. Yeah, we'll see when we get into it. It's been a while since I wrote this, but I do believe that this is the virtualized input because I have virtualized wrappers on my display, on my touch, and on my general purpose I/O. And the reason I virtualize that is so that I can have fake versions that I use when I run my simulation, and then real versions that I use when I'm running on actual hardware. But anyways, let's go. Display is OLED display. Yeah, I wonder why, like I'm using in this with statement, I'm creating touch and then my virtualized touch. I'm creating OLED, but I'm creating my virtualized OLED in here. I don't know if there's a reason for that. Doesn't matter. Then I create my actual state machine and I pass it the GPIO, virtualized interface, virtualized display interface, the virtualized touch interface, and the log interface for logging. That's the four things the state machine needs to run. And then we just have a while true loop. We're going to check to see if we're dying. If so, we break out of the loop. Otherwise, we read the state of the touch. We step the state machine by however much time has passed. And then we sleep for 0.1 seconds. So typically, this is going to be 0.1 seconds unless, something weird happened. There's a little hiccup. But that's the basic idea. It's just a loop that runs 10 times a second and runs the logic of the state machine at every point during that. So it's for the most part, it's not event-based. It's polling-based. But the interesting thing here is that this touch interface is event-based. So when you touch the touch interface, it sets up an interrupt. And I set up an interrupt handler that should read the state of the keys whenever it gets that interrupt and update it. The problem was that when I did that, it would get stuck. And I'd have to manually read it in order to get it back, which is weird because the interrupt reads the keys, so it should reset the interrupt flag internally when it does that. But it wasn't doing that. I don't know why. I have no idea why it doesn't do that. So my workaround was just, okay, at every tick, just read the touch, and that will reset the interrupt, and everything is fine then. It's a little annoying. It doesn't affect the program in any way. It still runs fine. It was just annoying for me. I made the whole key interface. I made it all, event-based with interrupts, and then it didn't work. So I don't know. But I was tired of trying to figure out why it wasn't working. And so I just read it at every tick and it works fine. But anyways, now we have a try here. And at the very top level here, we're catching exceptions and we're making sure that if bad things happen, we turn off the valve at least. So options for exceptions that come out: keyboard interrupt. If you press Control-C to end the program, especially if you're just running it manually, not running it from supervisor, that's not an error. We just want to leave. So we handle that exceptions specially. We log that we received the Control-C, and then we'll reach this finally where we'll say we're exiting, and we'll turn off the valve, clear the display, and return control back. But if we get any other kind of exception, we want to say, hey, we got an unhandled exception, log that exception's info. Also output that to, standard out. And then again, we'll say we're exiting and whatever. So this finally says, no matter how we leave this try catch, we're going to, print this log that we're exiting, and we're going to make sure we turn off the valve and we clear the display. And this means that no matter what kind of problem happens at what call stack, whenever that unexpected thing happens, it's going to throw an exception, because that's what everything does in Python. When something bad happens, it throws an exception. And that will propagate up here, and we'll make sure that the valve always gets turned off. And if we did not have exceptions, if we had to check return values on every single function that we called, like you do in C, it would only take one place where I forgot to check the return, and could screw up the whole works. So that is why I love exceptions for me. I love this for me here. And it works fine. It has worked, and it has in the past caught at one time. It did catch an error which could have potentially made my floor wet. So beautiful stuff. So that's the top level. So we can see here that all the heavy lifting is done here. State machine dot step. So let's go to our state machine, supply machine, and here we see it's a class. And yeah, it takes in all the things that it needs to interface with, the virtual interfaces for input output, for display, for touch, and logger. Sets those up. It tries to open a settings file. So I've got settings in, I don't know if I can see, is the file even in here somewhere? It should be a JSON file, yeah. So here I can set and right now the only settings are the timings for timing, when to fill and how long to fill the reservoir for. So I can tweak them without having to, change my Python code or whatever, just in this JSON file, which is nice. Yeah, so try to open that up. And in the step function, again, we have a try and catch. If we have an exception, we try to enter a panic state. So the default, when we get an exception, the default is actually not just to set the valve to false and cancel out. This is only really a final, if something really weird happened, we'll hit this one. Generally, what you're going to see is you get an exception in your logic here, and that tells you to enter the panic state. And then while you're in the panic state, you're not doing anything. You're just putting a panic message on the display. But if we get an exception in the panic state, then we would raise that exception, and it would propagate out to here, and we would exit. And once again, set the valve to false. But normally, a problem would just put us in the panic state. Yeah. So in here, what are we doing? What are we doing here? So I have something called a context object. That is the object that is passed to every individual state that it uses to do its work. Because every individual state has jobs that it needs to do. It needs to access, well, what does it need? It needs to access the I/O control, the display, the logging, settings, and touch. So instead of giving each state like a pointer or a reference back to the state machine that holds all these things, I don't want states to be, I want a top-down dependency hierarchy. So I want supply machine should be dependent on the abstract state, but it should not be dependent on any specific state except maybe the first state, the starting state that we enter. And no state should not have any concept of a supply machine. So we have a one-way, we don't have a circular dependence happening. You could do a circular dependence, but it's nicer if you don't. And by creating this context object, which just gives all the useful interfaces that a state would need to work, by creating this context object and passing it to each individual state, we can make sure that states don't have to couple to the state machine. A little bit of architecture there. So we create our context object. We get some state flags here. Check to see if the fail latch has been set, if the flood center has been set, if the hardware watchdog timer has been fired, and if we see any, let me see, type self.state is panic. So so now we're going to do some testing here. If our state is panic, just step, because if you're in a panic state, that's all you do. You don't look for anything else. You just run your state machine because you're stuck in panic. But if you're not in panic, okay, let's see if any of these bad flags have been set. If so, we're going to raise an exception saying we have detected on our sensors something bad, raise a panic exception. And that is going to hit here, and then we are going to transition state into panic. But if we raise an exception, like a panic exception, and we're already in the panic state, that's bad. You should never have an exception in panic because you're not doing anything in panic. So if you accept in panic, then we escalate to here, and we're just going to exit the program. But we're going to try once again to set the valve to false just to make sure. But again, that has never happened, and it probably never will. So if we're in panic, just step the panic state. If we detect a bad thing, raise a panic error. What is this? If 0 in context keys, so if the 0 key was pressed and we're not paused, we should immediately pause. So we should set the state to paused state. That's interesting. I think this might not be good now that I'm reviewing my own code. Instead of directly setting... okay, never mind. This is fine. We're saying the next state that we should transition to should be paused. So if we press the pause key, we should say we got to transition to the pause state. Otherwise, if we're not pressing the paused key, then we should step the state machine. We should step the state, whatever state we're in, we should run a tick, and the return value will be the next state that we should transition to. So if it returns none, that means that we shouldn't do any transition. We should just stay in the same state. But if the state that we've ticked, if it returns a state, then we should transition to that state. So that's what this works. Yeah, that's fine. So if we press 0, we should transition to paused. Otherwise, we should run a tick of our current state. And then if we have a next state to transition to, then we should transition to that next state. That's it. So essentially, most of this stuff, like in general operation, you're not in panic mode. You don't have a bad sensor. The user hasn't pressed the pause key. So in general operation, you run a tick, and if we should transition to a next state, you do the transition. That's it. So transition state, every state has hooks that it has defined for things that should happen when you leave that state, and things that should happen when you enter that state. So for transition state, you call on leave on the current state, you call on leave. And on leave gets knowledge of what the next state is going to be, and it gets the current context. Then we're going to log the state transition, because that's interesting information for me to look at later. And then we're going to call for the state that we're transitioning to, we're going to call on enter. And on enter gets information, again, the context and the current state that you're transitioning from. So you see these states, they have, nice hooks that you can define the behavior of, not just you define the behavior of every step, but also when you're transitioning from one state to another, you define that behavior, and it gets good information on what that transition looks like. What was the previous state you're transitioning from, and what is the state that you're going to transition to. And finally, for transition state, you set the current state to be the next state, and then you're done. You have made your transition. So let's quickly look at supply context. Yeah, it's basically just a struct is what it is, right? It just contains public, data members for all these different things. The current time, keys, settings, log, control, right? So it doesn't get direct access of the key input. It just gets a set of the keys that have been pressed in the current state. It gets the current time, yeah, all that stuff. And this is what each state will use to do its dirty work. So then we look at the state. Now the way that the state machine works is there's a machine object, and the machine object contains the current state. So there is a virtual interface. Python doesn't, it's just duck typed, but you can actually do like a kind of virtual functions and virtual inheritance in Python, I found, and so I did. So let's find supply state. So this is the virtual class. I don't know why I didn't mark these as abstract method. I think they should be abstract method. Oh no, it's not abstract method because it has a definition. So okay, yeah. So you can have a virtual class, and you do that by inheriting from ABC, which is abstract. I don't know what ABC stands for. I don't know, man. But every supply state will have a function to step, on enter, and on leave hooks. And this is just a function that every supply state uses. So I pushed it up to the parent class. It just as a helper display the elapsed time, because every state displays its elapsed time, so I didn't want to duplicate that code everywhere. So I pushed that up to the parent class. But yeah, on enter and on leave are overrided in the child, but they don't have to be overrided. The default is just they do nothing. So I don't mark it as an abstract method, because if you mark it as an abstract method, you're saying the child must override this, and if they don't, it's an error. And the only thing that every child must implement is the step. They have to implement their own step logic. But on enter and on leave by default can be empty, and it probably is in a lot of the states. So let's look at all the different states, I guess. So where do we start? I guess the running state. Oh, is there a start? Yeah, there is a start state. I don't know if I use it though. You see it all these states inherit from supply state, and this one, when you step it, it just transitions to running. So I don't know. There's no real reason to have a start state. But let's see if I'm actually using it or if I stopped using it. Let's go into supply machine. And let's look at what we initialize state to be. So display touch log. This is supply. State is equal to state.start. So I do initialize state to be the start state, apparently. And then once you do a single step, it'll transition to the running state. So when we enter the running state, we call on enter of the parent. Yeah, which doesn't do anything actually, but it's just a good practice to do that sort of thing in hooks, depending on how you're running your hook. We clear the display, and we write out text. We write out the name of our new state. That makes sense. Yeah. So this state name That's output. It's not we don't write the name of the state. We don't update the display at every step, at every tick. We only update it once at the beginning, and then we leave it. And that happens on enter. So that's when, we write out the new name of the state. Every step, all we do is we read the IO, and we see if our water level has gone low. And if it's gone low, we enter the low draining state. Because when we see the water level go low, there's actually still a little water left and the humidifier is still running. So we want to wait until we've drained that last amount out. And that's just a fixed waiting time. That's what the low draining state is. And then we do self display elapsed, which again is in, where is it? In supply state. And that just calculates the time elapsed and outputs that on the fourth line of the output. So low draining state. This one's got a little more juice to it, a little more sauce. Get duration. So here we have a helper, private helper function that tries to read the timing required, how long we should wait for low draining from our settings in our context. But if it doesn't exist in there, which is possible, if someone messed up their settings.json, we want to output a warning that our settings file is bad and use the default drain duration, which is 120 seconds. So we have a fallback. We don't just want to error out and stall our machine. If the settings file is wrong, we'll use a default, but we will put a warning in there to the user that, hey, you should probably update your settings because they're not good. So that's what this function is for. And when we step in low draining, on enter is the same as the other one. We clear the display and we output the new name of the low draining. So in step, what we're going to do is we're going to calculate the time elapsed in this state. We're going to calculate how much time is left in the state, which uses get duration. And if the level, when we're waiting in low draining, the level has gone low. If by some reason it goes back up high, we want to enter the running state again. And this is important because what can happen is, let's say I still have quite a bit of water left in my reservoir. And then there's an earthquake, which happens quite often in Japan, and the level sensor bounces. And so I've got a lot of water left, but the level sensor bounces and it detects a low level. So now I enter low draining. It waits for 120 seconds. It assumes the reservoir is now empty and it tries to fill it to full again. Only it wasn't empty. It just detected a low level periodically, instantaneously because of the earthquake. So now it's going to try to fill to full from empty, but it's not empty. So it's going to overflow my reservoir. And the solution to that is we put a test in the low draining. If it ever goes back to high, then we just go back to the running state and we wait for it to go low again. And that's easy. And that wasn't in my original C code in the version 1 of this, Mark 1. So, yeah. It was a nice little addition that I thought of, and it was a good idea. The chances of it causing an error, a problem, aren't super high, right? And you'd already have to be, even with an earthquake, you'd already have to be pretty low in order for it to bounce low during an earthquake, unless it was a massive earthquake, in which case you probably got bigger problems. But anyways, so even if it did flood, it would only be a little bit, but still, it's nice, and I'm glad I put it in there. So if the level somehow goes back high, we're going to go back to the normal running state. But if the remaining time has elapsed, if we're done waiting for it to drain, we enter low filling state. And then no matter what we're doing, we're going to update the display to show the remaining time. So some states, they only show the time elapsed in the state, but states that have a fixed time, they will also show the remaining time. And that's very nice for me when I was debugging this, because in the Mark 1, I had no idea of how much time was left. It's like, the watched pot never boils sort of thing. It was very annoying. And sometimes I'd be like dancing on my toes, because when it's actually, the valve is open and it's filling, you can see it getting higher and higher. And like, is it going to stop? Is it going to stop? How much time is left? Oh my God, should I pull the plug? Whereas if you have this remaining time display, it just helps your general cardiovascular health. And yeah, so that is that. Context display text self display elapsed. Oh yeah, so we're displaying elapsed every step. We have that in pretty much every state. Yeah, so this one transitions back to running if something weird happened, but usually it's going to just proceed to low filling state. And what low filling is going to do is, okay, the level sensor is low. We're going to open the valve. So when we enter this state, in addition to the normal stuff that we do, we're also going to open the valve. And what we're going to do is we're basically in the low filling state. Once it fills a little bit, the sensor that detects a low level will stop detecting a low level. That doesn't mean the tank is full. That just means it's filled up a little bit. So what we do is first we're waiting for just the low level to go to not low. And we wait for 7 seconds by default, or whatever setting is, in our settings file. Now, if we've waited 7 seconds and it still hasn't gone up, that usually means that there's no water left in the big reservoir. And so it's not filling up. And in that case, we have to enter a state that says, okay, the big reservoir is low. Let's, display a message to the user saying you got to fill that reservoir. But normally what will happen is after a certain amount of time, a few seconds, it will detect that we're no longer low, and then we will enter high filling state. That will be a timed fill to see, okay, you have to time how much time it takes basically to fill the small reservoir to full now. And yeah, that's basically what it is. And the way it works is we give it a 7-second timeout to fill enough to stop the low sensor from detecting a low level. But the total filling time is actually the time that's taken in this state plus the time in the high filling state. So it's interesting. So that's why we actually pass the start time of this state when we create the high filling state, because it needs to know the total filling time, because I want to cap the total filling time. I don't want to just cap the filling time in the high filling state. But anyways, that's neither here nor there. So you do low filling, it fills up a little bit. The sensor detects we're no longer mostly empty. So now we enter the high filling state. And the high filling state, where is that? Where's H? I know H is before I. There we go. And, again, there's a high filling time of 20 seconds. So what this says is that the total filling time should be 20 seconds. So the time in this state is 20 seconds minus the time we took in the low filling state. That's what it is. So get remaining time. Again, we just do that subtraction. And that subtraction calls get duration, which tries to get the settings from the file. And if not, falls back to the default. And when remaining time has timed out, we go back into the running state. And that's it. Now, in the case where the big reservoir is empty, we're going to go from low filling into low reservoir. Oh, one more interesting thing about low filling is on enter. When we leave the low filling state, if we're leaving the low filling state and we're entering any state that's not high filling, we also turn the valve false. So that's where this comes in. On enter and on leave, they get information about the previous state and the next state. And in this one, it actually uses that information to determine whether it should turn off the valve. So if we're going into high filling, we leave the valve on. But if we're going into any other state, we turn that shit off. So if an exception happens and we leave this state and to enter the panic state, we turn off the valve. Or if we leave this state to enter the low reservoir state, we turn off the valve. And I love this this design that I've made here, where these hooks, they get their context information and additional context about the states. I like this design that I've come up with here, and I might use it again like in a C++ project that uses a state machine. But yeah, so if this sensor doesn't stop signaling low level and we time out, that means that probably the top reservoir is either empty or a sensor has failed, which is also bad. But either way, we're going to enter the low reservoir state. And in this state, when we enter it, reservoir, we put out a message to the user, tank is low, so refill the tank and then press the refill button, which is button 1, to resume. And all that low reservoir is doing is it's waiting for the user to press the human refill button. So it just sticks out in this state, and it tells you how long it's been stuck in this state, which is useful. You can tell how long the humidifier has been stalled because some human needs to add water. But yeah, that's basically the flow. That's the whole state flow. Now, there's also a state. Let me see. Are there any states? I mean, there's a state in here. There's the panic state. So let's look at panic. And what it does is when you enter the panic state, it also sets the valve to false. So normally, this wouldn't even be necessary, because when you leave the low filling, it'll set it to false. Or if you leave the high filling, it'll also set it to false. But just to be super safe, when you enter the panic, it also sets it to false. Clears, outputs panic, outputs some information about the sensors. So if the exception that caused this panic, if that exception was a panic exception, a sensor panic error, then we're going to output the actual data, the flags that were set to cause that panic. And yeah, we output that information and nothing else happens here. When you enter a panic, I don't even give you the option of pressing a button to get out of panic. But I mean, I could add that in there. It's just, it hasn't, because I don't ever enter panic. So it's such a rare occurrence that it's not even worth it to me. But yeah, I could add like a option for the user to use the interface to reset it if they fix the problem. But right now, you just basically, you have to restart the program. The other state is the pause state. So if you hit the pause key, you enter the pause state. And in the pause state, all it does is it displays a user interface that says you can press this key to resume, and you can press this key to manually control the filling. And this is obviously useful when you're doing something like, let's say you're cleaning the small reservoir. You got to pull that out. You've got the tube just hanging out. You don't want the humidifier, the control unit, to start dumping water out. Say, it's time to fill the small reservoir. Goosh, swoosh, and you get a bunch of water on your floor. So you pause it whenever you want to do some maintenance or whatever like that. This is nice because before, whenever I wanted to do that, I just had to pull the plug out of the wall. So this is better. But yeah, it's a very simple state. And that is that. I think that's pretty much all the states. Not a big deal. It's enough that I didn't even draw a diagram for it. It might help to show a diagram, but I'm not going to do that. Come on. So what else is left? Okay, so there is one main thing left, and that is in the context. So let's look at the supply context. So you see we have the I/O control, the display. We also have the input. Where are keys? So keys is a set, but there's the keyboard input. These things, they all have a virtualized interface with a fake implementation and a real implementation. So the virtualized ones are the display. Very simple interface. Get the number of pages on the display, basically the number of lines, column count, clear the display, and output text to a location on the display. These are the 4 abstract methods exposed by display. And this is all that the state machine and each state is aware of. The input, where is the input? Let me see, what is it called? Probably mtouch input. Which one is this one? Okay, so this one is the real implementation of the input, which I guess is probably going to be called touch. Yeah. No? Yeah, I don't know which. I'm not sure which one is which. So I think touch is just my wrapper around the physical machine. So this encapsulates all that control codes and all that happy horse crap. Touch input is my abstract. Okay. So the abstract one, touch input, has only one method, pop keys. So this just reads whatever key presses that have happened since the last time I called pop keys is basically what happens. And it just returns a set of whatever keys were pressed. And that's it. Very simple abstract interface, hiding very complicated implementation with the actual hardware. So that's the display, the touch input, and I/O control is we get the low-level sensor reading, we get the flood sensor, we get the valve, we get the failure latch, and we get the watchdog timer. So set valve. There's also one to set valve, not get valve. We set valve. So there's 4 sensor readings, just return a flag, and 1 function to set the control the valve. And that's all that is. And then we have fake versions of them, like for example, fake I/O. And that just basically maintains the state of each one of those things in some member data, and then allows us to control them by imposing values and getting those values. The implementations just return the values stored in here. Very simple, right? Fake display, when we write text out, it's just going to print that information out to standard out. That's all that is. And this Python special function repr, that just means that this is the string that will be represented by this current object, the self object, when it gets printed. So when I print self, it actually calls this function, and that just basically formats how the display would look like, and formats that to a string that can be printed to standard out. And the fake, what is the other one? I did the fake. So the fake touch input. What this does is, okay, so it has a function press key. So what I can do is, when I'm in my simulator, when I read I just basically do a scanf, read a value from standard in, I call press key, and that it will add that to the set of keys that this thing will return when we call pop keys on it. So this basically just exposes a way for us to connect this pop keys interface to something like a standard input. That's the fake interface. Now the real interfaces, they get quite complicated. I don't want to go into too much detail. They're very specific to the different boards that I'm using. I've actually shown a lot of that stuff in my previous videos when I had it in C code, and I basically just took that C code and translated it into Python. So for example, let's look at GPIO control. So this implements the virtual interface, IO control. It gets all these and sets floods, and all this does is, let me see here. So when you construct this, well, this is where the mapping happens. It maps what signals map to what pins on the Python general purpose IO. So that's what these bad boys are in here for. I could put this into the setting file if I wanted to be frisky about it, but I'm not gonna do that. And what we're gonna do is for each of these pins, we want to set the mode if it's input and output. We want to set the pull up, pull down state of each one of these pins. We're going to make sure that the valve, when we initialize this, the valve is off to begin with. And then, for each one of these, we just call into the PigPio client and, read values from those pins or write a value to those pins. So that's all that is. Not too complicated for the general purpose IO. What else do we have? So the real implementation of the input. So there's touch. So touch input is the abstract. There's touch, and then there's M touch input. So which one is which? Okay, so touch has some very low level details. It uses PigPio to do I2C communication with my M121 board, I believe it's called. Yeah, MPR 121. And so it sets up, it just does all this configuration initially to set up the keys. Honestly, I couldn't tell you what all these settings are for. They're for thresholds for touch and release on the capacitive sensors, but I just got these values somewhere. Originally probably from some C code, actually, and then translated it into Python. Now, one interesting thing here, perhaps. Let me see here. On enter, on exit. So yeah, we open a I2C connection here, and we close it on exit. Read state. Now, we have a single function here that allows us to read the state of the keys, and that returns a bit string. So I decided to, I spent some time figuring out how I wanted to encode this stuff, and I ended up with bit string, whatever. We get 12 bits because there are 12 electrodes on the capacitive input, and that's the only real thing that this thing exposes. So it does all the initialization, and we have self connection. So the connection here, what is connection? That's just I2C stuff. And in here, yeah, we're just reading from address 0 in the device, which gives us the state of the bits. We read, 16-bit value, but only the first 12 bits are valid, and then we return that as a bit string. So now the question is, what does the other touch one, the M touch input, what does this one do? So this one is this is a low level. This is a high level wrapper around that. So we import touch input. We also import touch, which is strange because I think, no, it is not strange because that's the virtual interface that we're implementing. Yeah, okay. So we inherit from touch input, which is the virtual, and we're using touch as a low-level implementation. And what we do here is there's a pop keys function. Yeah. So here's where we set up that IRQ. And what should happen is when the user when it touches the sensor, the IRQ goes high. That calls this callback. And then we should read the sensor. Reading the sensor should reset the IRQ line. But that wasn't happening for some reason. So I could detect that the callback was being called and I was getting it, but the IRQ would stay high and we would never be able to re-trigger it. So yeah, and I didn't know why that was the case. And my solution to that was, okay, in main, I import the, not only the, so I use the raw touch, not the virtualized one, the raw one to read the state at every tick. And that makes sure that the IRQ gets reset. Why it does not get reset? Maybe it's happening too fast. But I'm pretty sure I tried to put like a delay. Where was I? I was on I2C GPIO. Here. Like I think I even tried to put like a delay or something. But it wouldn't work. And a delay is kind of bad as well because you want to read that sensor state at the instance when the IRQ was triggered. Otherwise, you won't get a valid reading for that IRQ, right? But anyways, that's how that works. So this thing actually wraps it all up. It maintains the set of keys that were pressed, and it sets up and maintains the callback IRQ from PigBio. There you go. That's the input. Mildly complicated, especially like this is just a lot of stuff, right? This is a lot of stuff that involves reading and experimenting with data sheets that were written by people whose first language is not English. So the last thing is the display. And that is, so there's OLED display. That is the virtualized one. There's fake display. Yep. And there is OLED. This one is the low-level implementation of OLED, which gives us functions like set the position of the cursor, write some columns of data, write a page of data, which is just a line, to be clear. Don't ask me why I didn't put write line. It's weird. Clear the entire display. Fill the entire display with just an array of pages, basically. Or just a whole byte array that is the whole buffer of the screen. So we get like a bunch of useful functions to interact with it. It also encodes the procedure for initializing the display. And what is this? In here I also have my text writer class, just private to the OLED here. Or maybe not private, but it's in the OLED. And has options for outputting a character. Output is string. Output string at. So this one, when you create a text writer, it maintains a reference to an OLED. And these functions will then write character information to that OLED. This is graphical information about the fonts. So each one of these is a glyph. And that gets translated into from ASCII into one of these, and then these get written out into the display. And then the OLED display uses, no, wrong. OLED display is this one implements the display virtual interface and uses the OLED object. And then so for clear, we just call OLED.clear. And for text out, we just OLED text output string at. And that's it. There you have it. So that is all that virtualized stuff and all the low-level implementation, high-level implementation, fake implementation. Now, the beauty of that virtualized interface is if we go back, and I pretty much covered now all the classes in here. So I've covered all these files. But if we go back into main, if I can find main, I've got do simulation, which instead of go, what it's going to do is it's going to create for display, it's going to create a fake display. For touch, it's going to create a fake touch. For control, it's going to create a fake I/O control. Then it's going to create a supply machine, same supply machine, but now we're passing them fake stuff for everything. Well, log is still just a log, so that's fine. And now, while we're not exiting, what we're going to do is we're going to take some input from the user, and if the in is an S, we're going to step time by that amount of time. So we're going to call machine.step in a loop. And we have commands for setting the level low, for setting level high, for signaling a flood. If we just press enter, we're going to step by 0.1 seconds. If we press B, something, we can, so B is, I don't know why I called it B. Why is it called B? But B means for a key press. B seems like, why is it not K? I don't know. Weird. Sometimes things are just weird. But anyways, B means key number B was pressed, so we're going to call touch.pressKey. And T means, I think that's like trace. So print out the state of all of these fake peripherals and the current state. Q means quit. And there you go. So it's just does this input in a loop, and we can use these inputs to step time and run our state machine in a simulated manner. And I also have a function here. That one's just for testing the display, but this one's not used. So if I go into Go, obviously if I run this one right now, it's not going to work because I'm not running. Yeah, I'm not running on Python. So what it's going to say is it's going to be starting up, and then it's going to say cannot connect to PigPio because the PigPio service is not running because I'm not running on my Linux Python hardware. But what I can do is change this to do simulation. Simulation. Now it's not going to try to connect to PigPio, and so it's going to give me this prompt. Now I can input commands, so I can do T for trace. So now it tells me the state of my I/O. The low-level sensor is false, no flood, valve is off, watchdog timer low, latch low. This is what the screen looks like right now. And we're in the start state. The start state doesn't output anything, so empty display makes sense. So let's step time by 0.1 seconds. Now we are in the running state. I don't know why it didn't output the transition. Maybe I don't know. That doesn't matter. Anyways, so we've transitioned to running state. So if I do trace, it will say the state is now running, and the display has shown that we are in running. This is the set of keys that have currently been pressed. So for example, I could go B0. I've pressed the 0 key. Now if I trace, we see that the 0 key is in here. And then if I step the state machine by 0.1 seconds, now we're in the pause state. I can press B1 to resume. And if I step, we're back in the running state. And if I step again, you'll see now it has started outputting the elapsed time. So if I step by 10 seconds, we'll now see that 10 seconds have elapsed. You can see when I do this step, it actually outputs the screen every 0.1 seconds. So after some time has elapsed, if the humidifier is running, the small reservoir will go low. And now if we step time, we will see that we have entered the low drain state. So we're going to wait 480 seconds for the small reservoir to basically completely empty, to empty so much that the humidifiers now cannot suck water anymore. So let's step time by 479 seconds. So now low drain, there's 1.1 seconds remaining. So we can tick that down, 0.9, 0.8, 7, 6, 5, 4, 3, 2. And now we are in the low fill state. We can see that our state machine has set the valve to true. So the valve is now open. We could also verify this if we trace. We can see low level, sensor says true, flood is false, valve is true. And now if we were to step we could step, 5 seconds. And now normally what would happen is after, about 5 seconds, the low level sensor would show high. And now we're in high fill state. And it would continue then to fill, keep the valve open until, let's step for 15 seconds. And still, we're at high fill, 0.1 second, and then we transition back to running state, and the valve is set to false. So the valve is once again closed. And what else could we do? Well, we could simulate the top tank running out of water. So we'd go low, and then we'd wait for the low drain to finish, so 480 seconds. Now we are in low fill, and if the low fill times out, so if I step for 11 seconds, and it still hasn't gone high, that means, we're probably out of water. So then we enter, so we're low fill, valve, we close the valve, we say reservoir tank low, refill, and press 1 to resume. So this is basically printing out every line every time the display was updated. So then you would, you'd fill the top reservoir, you'd press the 1 button, and you'd go, and it would try again to fill, right? Because if this state happened, that means that the small reservoir is empty. So we should once again try to fill if the low, let me see here. If I trace, low level is still true, right? It wouldn't go high. So then we do low filling. Now what happens? Okay, so we go low filling. Let's step 5 seconds, just, to make it all above board. Then we go high. Now what happens during high fill? Let's step 10 seconds. For some reason, maybe we just get really good flow out of the tube one day for reasons unbeknownst. It overflows. So we would get a flood. What happens then? Well, we would enter the panic state. So when we leave the filling state, the valve is set to false. And then when we enter the panic state, it's once again set to false, just to be sure. And then we get a panic error telling us that the latch has been set and the flood sensor was triggered at the time that we received the panic error. And once we're in panic state, there's nothing we can do. We're just stuck. We're stuck in panic. And let's step 10 seconds. Yep. And we're just going to elapse in there. And let's see, if I press 0 button, does anything happen? Nope. You can't pause. You can't do anything. Panic means you're going to have some intervention, basically log in via Linux and SIGTERM, tell supervisor to reboot the process. But that's that. Let me see here. Can quit. Run it again. Can do B0. We're paused. We can do B2 and do manual filling. So when we press the button, valve is open to true. And if during manual filling we get a flood, I don't think I've ever tried this actually. Yeah, we get the panic. So even if the user tries to override it, we can't let the user flood the house manually. If the baby somehow figures out how to use the interface, they will be able to only get a small fill, not a big one. But that's that. That's basically that. And the ability to do the simulation in here without having to working on hardware meant I could do a lot more testing, and it meant that when I found problems and bugs, it was a lot easier for me to diagnose and iterate them. Having to work on real hardware and having to debug the real hardware was a much, much worse developer experience. I would say it increased the time it took me to fix problems and just to get the job done like 5 times, like I would say 5x more time. And that's not an overstatement. This is an amazing win for me. And this alone made the choice to use Linux like just banging. So not Linux, Python, so that I could simulate on my Windows environment and run on the real hardware with the same code base. So yeah, that's it. That's all she wrote. That's a lot. How much time has I been spending here talking? Well, about an hour. Okay. I had a little bit of a heart attack. I looked over at OBS and a timer said 0:00:00. I was like, did I not turn this shit on? But that was the streaming live timer. The recording timer says 1 hour and 7 minutes. And I imagine there will be a little bit of cutting down, but not too much. And I'm probably just going to, on the end of this video, I'm just going to tack on the remaining little footage that I had recorded just while building the hardware and everything that I didn't really fit into any other video. So for people who are, who are super interested, it's a minority, but there are some people who enjoy this series. So for you guys, I will put I'll just edit the video in there at the end and call it a day. But yeah, that's it. That's the end of this. And that's probably the end of the videos on this project, this topic, unless I find something super interesting and I have the time and the bandwidth and I find it's worthwhile. But probably this is the last one. So thanks for coming with me on this journey. It's been quite a while, and it's been a little, separated from the actual stuff, because this was actually finished, a year and a half ago, basically, almost a year and a half ago. So the report has been a little late, but it's here now. And yeah, if you want to, you can hit me up in the comments or in Discord. You can tell me what you think about the stuff. I'm pretty pleased with this code base here. I gotta say, I like the approach to the state machine. I don't think it's the right approach for a lot of other, for every project, because I know a lot of state machine libraries that I look at, they kind of have a way of defining the state transitions globally on a tabular level. And I think that might actually be better for super complex state machines. But for a simple enough state machine, the ability to basically encapsulate all the logic for a state in that state's own, file, class, for example, the low filling state or whatever, to encapsulate what happens when you enter, what happens when you leave, and how the transitions are managed. It's very nice, at least for this use case. So I like it, and I will probably use it in the future in a C++ context. But yeah, thanks for coming along, and I'll see you. I'll see you when I see you, and we'll be doing more stuff, more C++ kind of stuff. But I will leave you off with some videos of hardware shenanigans. Ta-ta. Alright, check it out. I got my sensor here and got it hooked up. I don't know if you can see here. Yeah, I got it hooked up to the main unit in here. See, the main unit is running right now. It's on low drain, so it's detected at a low level. It's waiting for the thing to drain out, to bottom out, basically. And I got the level sensor hooked up to this push button switch here. So if I push the push button, if it's in low drain, but then it detects high level again, it goes back to normal running mode. So a little bit of a improvement over the last behavior there. But yeah, inside the box, oh, you can't open up, you bastard. Inside the box here, we got all the goodies. Oh yeah. On the breadboard here is mostly just the safety stuff, and also the I2C bus. And then here we got the power module here that I soldered up myself. And here we have, you know, the Raspberry Pi Zero. So yeah. So, but anyways, yeah. So I got the sensor here. You can see we're running normally. Now let me short out. I'm not gonna wet it because then I have to remake the sensor. This is basically a one-use deal. Once it gets wet, you probably just want to remake it. But if I look inside here, see I got one electrode. I'm just gonna hook up a wire. I'm just gonna put some wire on this bad boy. You can't see because I can't do that while I'm holding the phone properly. But so I got one side on the wire. It's hard to short this out. I don't have enough hands to freaking view this. This is why I don't record on my phone. This is why I use freaking Camtasia Studio or OBS, because I can't be fricked to hold a phone or mount a phone. But yeah, so I can short this out here. And if I can get contact between electrodes here. Okay. Yeah, that's not making contact, is it? You need to be there. Okay. And now you need to be here. Alright, now we got contact. Now if we look here, we can see, yeah. So when it tripped the, I don't know if this is going to focus properly. Please focus, you dumb bastard. You're not going to do it, are you? Yeah, you can see sensor panic error. So that's the exception that caused the panic state. And on the left, we see T for what tripped the error. And then on the right is, I believe, I don't know what that is. Is that a C? I can't remember, but that's the current state anyways. So what the state was when the error got tripped and what it is currently. And currently, the latch is the only thing that is problem. But the thing that tripped it was the latch and the flood sensor. The flood sensor tripped the latch, and one of those caused the bad boy here. So if I short this out again, now you can see it's saying, oh yeah, you still got flood. So you can see what happened, what caused the panic state, but you can also see what the status is right now. Because the flood sensor might dry and then go off again, but yeah, you see. All right, good stuff, good stuff. Everything seems to be working. Now, I'm going to hook it up and do a bit of a test. Alright, check this out. Yeah, I got the water level down real low here. Just to the point where I'm like, you know, it trips the sensor here. So it says low drain. Oh, yeah, there we go. It says low drain. So it's saying, yeah, level's low and it's waiting for just the remaining to be drained. Normally the humidifier would run for a little bit longer after my sensor detects the low level. So anyways, so I got that down there. It's kind of cool. I can push this thing here and bring it back up to high level. And if I show you my screen here, modified the logic just a little bit so that now if it's in low drain mode but it detects a high level again, it goes back to just normal running mode. And that's important because we get a lot of earthquakes here. So what can happen is the earthquake can shake the water and it can detect a low level even though it's not actually low, and then it'll go back up to high. But if my state machine doesn't allow it to go back into this state, then it'll run and then it'll start, feeding out water even though it's not actually low, and it might cause an overflow. So that's kind of cool. But yeah, everything seems to be working. Had some problems with my my valve here, because I had it sitting for about a year, and then I started up and like there was barely a trickle that came out. So I realized, I'm guessing that somehow some kind of air bubble got trapped in here, and it was preventing the flow, because I did some siphoning, and I took the whatchamacallit here, the hose, and brought the level up nice and high so that it kind of backflowed into the tank, and it seems to be working good now. Got good flow, so yeah, my test here. I'm gonna test the timing again for how long it takes to fill, and adjust my timings now. Now I got I can adjust them in a config file, so I don't have to reprogram and compile and reprogram the pick like before. Now I can just change a config file. Just log into my Linux server on the Pi Zero, change a config file, and it will be the new timings. So we'll see. All right, this is after 30 seconds of filling, which is the amount that I had before. And as you can see, it's like basically right to the brim. It actually overflowed just a little bit. So, and I think the reason for that is, if you look here where the hose is fed in, what I've actually done here, let me see if I can get it here, is I've drilled a little bit out of the plastic up there. So you can see there was more plastic. It went down to the hole level, a straight line. And it wasn't wide enough to accommodate this hose, so the hose got pinched, and that reduced the flow rate. So I think I got a better flow rate now, so I got to reduce my timing by a little bit, and adjust some other things. Like I got to adjust my watchdog timer, make it a little lower then. But yeah, we'll get back on it.